Okay, L'Hopital's rule also applies to quotients that lead to an indeterminate form of infinity over infinity. If f of x and g of x both approach infinity as x approaches a particular number, then just like the indeterminate form 0 over 0, the limit as x approaches a of f of x divided by g of x is the same thing as the limit as x approaches a of f prime of x divided by g prime of x. So just like for 0 over 0, if we have infinity over infinity, then we do the same thing, and we take the derivative of the numerator and the derivative of the denominator. Let's take a look at a couple of examples. If we look at this one, number 8, first let's plug in and make sure that we have this indeterminate form, and we will have 1 plus the secant of pi over 2 divided by the tangent of pi over 2. Pi over 2 is right up here. Secant of pi over 2 is 1 over cosine. Cosine at pi over 2 is 0, so this is 1 over 0. 1 over 0, just like before when we did limits, a number over 0 is heading toward positive or negative infinity. So we have an infinity here plus 1. And same thing down here, this tangent sine over cosine at that spot is going to infinity. So this is an infinity over an infinity situation. So if we do L'Hopital's rule, we're going to do the derivative of the numerator and the derivative of the denominator. Don't lose that limit part. That's important. The limit as x approaches pi over 2. Now I do the derivative of the numerator. Derivative of 1's 0. Derivative of secant x tangent x. Derivative of the denominator, secant squared x. One of these secants is going to divide out. So we're left with the limit as x approaches pi over 2 of tangent x over secant x. Let's see if we can simplify that a bit. Let's see, tangent is sine over cosine. Over secant, which is 1 over cosine. Hey, what happens here? The cosines divide out. And this all simplifies down to be the limit as x approaches pi over 2 of sine x, which is 1. We can sub in now and we get 1. And there we go. If we look at number 9, the limit as x approaches infinity, look at the numerator. As x gets large, that piece definitely is going to infinity. As x gets large here in the denominator, definitely going to infinity. So we are having an infinity over infinity situation. So we can do limits of the numerator and limits of the denominator. The limit as x approaches infinity of 5x squared minus 3x, let's see, that's 10x minus 3. Denominator, 14x. If we sub in, or if we do this limit again, we have another infinity over infinity situation. So this is L'Hopital's rule here. This is another infinity over infinity. So we'll do another L'Hopital's rule. And we have the limit as x approaches infinity of 10 over 14. Hey, that's a constant. 5/7. Some of you may have noticed when we started this problem that we could have done this problem much easier than L'Hopital's rule. If you recognize the limit as x approaches infinity, when the degree of the numerator is exactly the same as the degree of the denominator, we can just take the fraction of the leading coefficients, which is 5/7. But if you forget that nifty little rule idea, then you can definitely use L'Hopital's rule. And the neat thing about math, once again, is that as long as you do mathematically valid procedures, you get the same answer every single time. All right, that takes care of the indeterminate form, infinity over infinity. We have another indeterminate form, or two other ones right here. There is the infinity times 0 or infinity minus infinity. If this happens, we can use algebra to rewrite these somehow to get a 0 over 0 or infinity over infinity, and then use L'Hopital's rule. All right, let's look at this one. With this infinity, it's kind of hard here to try and substitute in, but this piece right here is infinity times tangent 1 over infinity is, that's like the tangent 1 over infinity, that's 0. So that's like the tangent of 0, which is 0. So we have an infinity times 0 situation. So what we're going to do is take this expression and rewrite it. Now you might not see it right away, but be patient with me. What if I rewrote this as the tangent of 1 over x divided by 1 over x? Isn't dividing by 1 over x the same thing as multiplying by its reciprocal or multiplying by x? It is. So now when we sub in and look at this situation, we do have a tangent of 1 over infinity. That's tangent of 0, tangent 0. This is 0 over 1 over infinity. That's 0. We have a 0 over 0 situation when we sub in. So let's do L'Hopital's rule. And we'll do a derivative of the numerator and a derivative of the denominator. So we have the limit as x approaches infinity. The derivative of tangent is secant squared. Times the derivative of 1 over x. I'm going to come up here. The 1 over x is x to the negative 1. And the derivative of that is negative 1 x to the negative 2. I'm going to write it back as a fraction. So negative 1 over x squared. In the denominator, the derivative of a 1 over x, well, that's the same thing. Negative 1 over x squared. These guys divide out. And we're left with the limit as x approaches infinity of secant squared of 1 over, oops, I didn't mean to write the infinity there, I'm sorry, 1 over x. I think I was thinking ahead of the game and substituting the infinity in for x in my head. So if we substitute in now, we get 1 over infinity, which is 0. So this is like thinking secant squared of 0, which is 1 over cosine of 0 squared. That arrow keeps getting in the way, which is 1. Done. Good boy. All right, one more with this indeterminate form. This one, the limit as x approaches infinity of the natural log of 2x minus the natural log of x plus 1. Remembering that the general shape of a natural log function looks like that. So as x gets large, so does the value of this natural log function. This keeps going up forever and ever and ever. So as x gets large, each of these pieces also goes to infinity. But we have to rewrite this. We can't just do L'Hopital's rule now. We have to rewrite it to get a 0 over 0 or an infinity over 0. And, let's use our log rules and stick these two back together as a single log. So we'll have the limit as x approaches infinity of ln 2x over x plus 1. All right, now the limit of a log function, really what we have to do is we have to find out what this piece in here is doing. Then we know the log of that, that's the limit. So we're going to kind of rearrange this a bit. I'm just going to kind of swap these. And we're going to do the natural log of the limit as x approaches infinity of 2x over x plus 1. Now when we sub in, we look at this. This is an infinity over infinity situation. So we can do L'Hopital's rule, which is going to be the natural log. Now I'm doing this L'Hopital's rule inside of here. Limit as x approaches infinity of 2 over 1. And the limit as x approaches infinity of 2 is just a 2. So we have ln 2. And that's it. Okay? Please join me on page 4 for 1 or 2 more indeterminate forms. 3 more. Whew. 3 more, but only 2 examples. So pick up with me on the next page. Thank you.